Hello and welcome. I'm going to be talking to you about my turn to teach about one of the topics that we learned in embedded systems. So, without wasting any more time, let's go. So, what is embedded systems or embedded programming? Embedded programming involves programming small computers that drive devices. So, what you're doing is you're programming on the bottom right hand corner is a picture of a Arduino Uno. That's a very typical small computer that you program to do many different things. So some of the practical implementations are it's useful in the design of software for automotive features, small facilities, handling devices like thermostats, and handheld games or other small devices. So anything that's small and that's easy to program and use something to drive that device is what we use programming systems or embedded programming. So embedded systems, it's basically a computer system, and that computer system is a combination of the computer processor, computer memory, and the input and output devices. It also dictates functions within a larger mechanism, within a larger mechanical or electrical system. So basically, it's like a brain that you can set it or program it to do multiple different things, like use a joystick to make a motor go forward or backwards, basically make a little car out of it, make a button out of it. You can do many different things. Like in the picture showing, you can use it to set your house, to automate your car, automate your house and your lights and other different things. So some of the key techniques that we learned throughout the class were pulse manipulation, bit twiddling, timers, interrupts, pulse width modulation or PWM, analog to digital conversion or ADC, serial communication, SIP communication, and I2C basics. So the picture is a basic scheme of embedded systems where user space and user interface is at the top, the application software, and then the OS and the RTOS. That's basically the programming software where the developers see it, but not the users see it. And then the hardware. So what I'm going to be talking about is timers. So timers is a specialized type of clock which is used to measure time in intervals. A timer that counts from 0 upwards for measuring time elapsed is often called a stopwatch. It is a device that counts down from a specific time interval and used to generate a time delay. For example, a hourglass is a type of timer. So the register increments for every machine cycle. So for a while loop, if you have the increment at the bottom, then it will go through the steps in the code, and then when it gets to the bottom, it will increment or add to the time. So the maximum count rate is 1/12 of the oscillar frequency, and a timer uses the frequency of the internal clock and generates a delay. So the pictures kind of show like how a timer works from the hardware to the software and then to the output, and it does many different things as it goes on. So a timer in a 8051 microcontroller. On the picture to the right is a 8051 microcontroller, and you can see the different pins and the different things that it can do. So this type of controller has two timers, timer 0 and timer 1. They can be used as timers or as event counters. So when something happens, it can count that event. Both timer 0 and timer 1 are 16-bit wide, are 16-bit wide. Basically saying that to activate the timer you have to use the 16 bits, or you can use up to 16 bits. Since the 8051 follows a 8-bit archetype, each 16-bit is accessed as two separate registers of low byte and high bit and high byte. Let's go next. So, the timer 0. The 16-bit register of timer 0 is accessed as low and high byte. The low byte register is called TL0, or timer 0 low byte, and the high byte registered is called TH0, or timer 0 high byte. These registers can be accessed like any other register. For example, the instruction MOVTL0 number 4H moves a value into the low byte of timer 0. So the picture kind of shows how it looks like, but for a developer we won't see that. We will just know that that's how it is, and then we program it accordingly. And a timer 1 is very much the same as timer 2. It's also a 16-bit, timer 1 is the same as timer 0. It is also a 16-bit register. It is accessed as low and then high byte. The low byte register is called TL1 and the high byte is called TH1. The register can be accessed like any other register, and then the same thing will we move the value into the low bit of timer 1 if you follow the example. It's very much the same as the other one. So the timer mode register, or TMOD. Both timer 0 and timer 1 uses the same register to set the various timer operation modules. It is a 8-bit register in which the lower 4 bits are set aside for timer 0 and the upper 4 bits for timer 1. In each case, the lower 2 bits are used to set the timer mode in advance, and the upper 2 bits are used to set the location of the timer. And then the picture just shows a basic how it's going to look to the programmer or to the hardware. You can have the input and then the output, and then you're going to set where it's going to show up. Conclusion. The timer is an important application in embedded systems. It maintains the timing of an operation in sync with a system clock or the external clock. The timer has so many applications, such as measure time generating delays. They can also be used to generate rates. So basically, timers are just one of the many ways to embed systems to do many different things. You can use timers to set the Arduino Uno to delay a certain action or count a certain action and then do other actions with them. And timers are just one of the many different ways to use embedded systems. Thank you for watching, and I hope you have a great rest of the day.